So last time we did Yule-Walker equations, so before we start an example, so I have here a Remus sim in R. So I'm going to simulate with
what is a Remus sim?
autoregressive integrated moving average model. Sim stands for simulation. So AR at 2 coefficients, 0.9 and 0.4. It works, didn't. Looks like that works. So clearly that is the PACF. And we can see from the PACF we have values of 0.65 over there, negative 0.4 over here. Now, if we go back to the autocorrelation function, it has 0.645 for row 1 and 0.183 for row 2. Good. So let's take a note of that. 0.645 row 1, 0.183 row 2. We simulated the series. We've got row 1 and row 2. Row 1 is 0.645, row 2 0.183. From last time, we know Yule-Walker equations. How do they go? Row 1 is equal to
Theta 1.
theta 1.
No, V1. Wait, I probably won't get it all wrong.
The Yule-Walker equations, I believe, row 1 plus V1, row 2. Missing something here. I believe that's V1.
That's what I was going with. And you said no.
So go ahead, let's see what he said. Go ahead.
You already put it there, so I don't need to.
Now our goal is to estimate the value of the coefficients. Of course, we could use system of linear equations, do it manually and all that stuff, but there is an easier way, which we did a long time ago, using matrices. So in terms of a matrix, this one would be row 1, row 2. And I can write that as 1, row 1, row 1, row 2, multiplied by V1, V2. If you recall from way back when, beginning of the semester, I showed you how to multiply matrices and vectors. So if you multiply that row vector by that column vector, you'll get that. If you multiply that row vector by that column vector, you will get that, and that equals row 1, row 2. Good?
It's also for the math, of course.
In our case, we have row 1 to the 0.645, row 2, 0.183. Row 1 is 0.645, 0.645, 0.183. V1 and V2.
You're right.
All right. So if I call this to be A, and that's as B, A equals B multiplied by V later. I can solve for phi if I multiply by the inverse. So B inverse A would be equal to B inverse times B. B inverse times B is just identity, so it's become 1. So B inverse times A would simply be equal to phi. So let's see, oops. We're going to start with the matrix A. So the second x in this. Going to edit matrix A. Matrix A is simply the vector that I had on the left-hand side. 2 rows, 1 column, so 2 by 1. The first row, the value is 0.645. Row 1, row 2, 0.183. So we're done with matrix A. Second mode to exit. Second x inverse, that's the matrix. Over to edit. Number 2. We need a 2 by 2 matrix. So 2, 2. And the elements are 1. 0.645, 0.645, 0.183. Good. Second mode to exit. So now, in order to find phi, we just need to do B inverse multiplied by A. So second matrix, select number 2. That'll bring up B. Press the X inverse button right there. Inverse. Second matrix, select A. So we've got B inverse A. Good.
I think I did it backwards and it didn't work, but
Huh?
I actually did A, B inverse rather than B inverse A, that didn't work.
So I get B inverse A to be 0 and 1. That doesn't make sense. So of course when we did, we got 0 and 1. Do you know why? Huh?
Oh, because the 6 more by next one.
Right, this column is exactly the same as the solution, right? So, of course, it's going, since this vector is in the solution space, you would expect to get 0 and 1. Which is why I stopped and I said, well, something must be off. I wrote the thing wrong, so let's just skip 2.
So that means that.
You're supposed to correct me unless.
You're a professor, I thought you knew what you were doing.
So, row 2 equals V1, row 1, and then 1. So change that to 1. And now invert it and tell me what you get. So edit your matrix B, change the second element, the 0.183 to 1. Follow the same steps B inverse A and tell me what you get for B. So when we inverted it, we ended up getting phi, which is phi1, phi2, 0.902 and
Negative 0.399.
negative 0.399. Good. Now, let's go back to our original simulation and see if these definitions match what I had in my simulation. So let's say for x and got the correct phase. The fee ended up being 0.902 and negative 0.399.
Yes.
I got that based on the ACF that I observed. I didn't even go in any further. All I did is I looked at the ACF. So the actual values were 0.9 and negative 0.4.
So very.
The estimated values are 0.902 and negative 0.399. Did we do a good job at estimating?
Yes.
Yes. So Yule-Walker is a great estimation technique. The fitted model here, or the fitted AR2 model to be specific, that's what we will have. Good. Now we can find the side rates like we always do. The characteristic polynomial is figure z. And what is figure z? It would simply be 1 minus 0.902 z plus 0.399 z squared. Let's get to steps you should know by now as to how we go from here to there. We simply move these terms to the other side, rewrite it in terms of the lag operator, replace the lag operator by z, pull the yt out, and we end up getting that. Good. We'll then have to solve that equation. It is a second order polynomial, so set that equal to 0 and tell me what you get to the roots. Okay, so if you use the quadratic formula, we will find the roots. What are the roots?
1.13 plus 1.11i.
So 1.13 plus I multiplied by 1.11. Z2
Same thing, but
would be 1.13 minus I multiplied by 1.11. This is what I meant by roots appearing as conjugate powers. So we have 1.13, I 1.11 and 1.13 minus I 1.11, and in the or on the imaginary plane, both of those would lie outside the unit circle, right? The real part is outside, the imaginary is outside. So we would have a causal series. If you can invert the MA side, it is invertible. If you can invert the AR side and express it as MA infinity, then it is causal. So we can find lambda 1. What is lambda 1? Yes. And lambda 2 would be 1.13, oops, 1 over 1.13 minus I multiplied by 1.11. just have to find the one, the other would simply be the conjugate of what they have here. How do we solve
Hold on,
and find number one? Yes.
How did you get? Yeah, I got this for Michael.
Well, you used to do
So we have number one equals 1 over 1.3 plus I times 1.11. We want to find this as a complex number. How would we find it? Did you guys do complex math and pre-calculus?
I didn't even take pre-calculus here.
So you multiply and divide by the conjugate. Right. And you can see I'm not messing with lambda 2 at all because I don't have to. If I know lambda 1, I can find lambda 2. Lambda 2 would simply be the conjugate of lambda 1. Good. So the denominator, if you FOIL, it would simply end up being the real part squared plus the imaginary part squared. It'll just be the magnitude. So you would have 1.13 squared plus 1.11 squared. So put that in the calculator and tell me what the real and imaginary parts are. So,
That you actually taking it, dividing the whole thing as well.
right, so you're taking each part here, so the real part divided by the magnitude, imaginary part divided by the magnitude. You end up guessing this. And as I mentioned, this would simply be equal to, lambda 2 would simply be equal to the conjugate of this. So I don't even have to do that again. So I can simply write it as 0.45. That's I multiplied by 0.44. Good. The next step, to find the psi weights, we had to find, what did we have to find? What is that general expression for the size?
So psi k C1 lambda 1k plus C2 J lambda 2 J lambda.
No, that's if you have repeating roots.
Oh, okay.
We're not going to see that repeating. Now, this is used if we have real roots, but we don't have real roots. And if you go back and look at what we did last time, we did a derivation where we wrote psi j to be equal to, in terms of capital R, alpha, and beta. What was it?
It was C1 1 over R e to the I theta. No, it was a close bracket 2 alpha cosine theta j minus beta sine theta j.
Minus, there has to be a beta somewhere, right?
Yeah, minus beta sine theta j.
That is our expression. If you recall, comes from the original root. That's how I did my derivation. So R would be Z1 and not the inverse of Z1. So R would be the magnitude, which is square root of A squared plus B squared. So 1.13 squared plus 1.11 squared. And what do we get? And we're doing this and not that because this is fine if we had real roots. Since we don't have real roots, we're going to go with this. And I believe your textbook derives it using the inverted root, using the lambda values to get R. I'm using the actual root directly. Okay, yes.
Do you always use the addition I'm just trying, like, instead of the 1.13 minus the I, 1.11, you use the plus I, 1.11 is, like, you always use the.
What do you mean? Can't follow. What are you trying to say?
For the R.
We're simply taking the negative doesn't matter because I'm squaring, right?
Yeah.
The magnitude is simply the square root of the real part squared plus the imaginary part squared.
Okay.
Yeah, so real part, imaginary part squared. What do we get?
1.584.
1.584. So we're almost done with side A here.
I forgot that R was a
So side A is 1 divided by 1.584 raised J. 2 alpha cosine theta J.
minus beta,
It's just beta or 2 beta?
just beta.
How do we find theta? We need to know the value of theta now. And finally, alpha and beta.
Would be 10 and sum.
So, can't be just beta, it should be 2. Because we got the alpha and beta from the C1 and the C2.
No, but do you have just beta as well?
Yeah.
I know that.
So, do make that correction though, it has to be 2 beta basic algebra. So last time, I don't know why I put beta, I just don't.
Really, we can't trust your numbers.
Perfect. Should be 2 beta.
I'm gonna give them a net now.
So theta is simply tangent inverse of B over A. Once again, the B and the A that I'm using come from the actual root, Z. So tangent inverse of what is B? 1.11 divided by 1.13. Yes. So 44.5, that's in degrees. But we want to convert it to radians, so in radians, how much is it?
.776.
Good. So theta happens to be 0.776. So we've got the other part filled out here, so we have 2 divided by 1.584 raised j. Alpha cosine 0.776j. Make sure it is in.
Where do you get the 2 from? Oh, you pulled up the 2, okay, never mind.
0.776j. Good. We found pretty much everything, and last time we did the tricks that we did with alpha plus I beta, alpha minus I beta, because we wanted a real valued expression for psi j. So all that is missing is alpha and beta, right? If you go back and look at my derivation, I said we can say alpha and beta, or excuse me, we can call C1 and C2 to be equal to some arbitrary complex number, alpha plus I beta, correct? That's where I started. If C1 is alpha plus I beta, C2 would be alpha minus I beta, and everything fell in place from that. So if I find C1, that is all I need to know, because once I find C1, I will know C2 directly. Do you agree? Because they are conjugates of each other. And we know from a long, long time ago, the formula for C1, which is lambda 1 divided by lambda 1 minus lambda 2. Agreed? So what is lambda 1? 0.45. Was it plus or minus? Lambda 1. Minus I 0.44 divided by 0.45 minus I 0.44. Lambda 2 is simply the conjugate of lambda 1, so minus 0.45 plus I 0.44. Good. This figure will have 0.45 minus I 0.44 divided by 0.45 minus I 0.44 minus 0.45 plus I 0.44. Those two. That's my story. Getting too excited here to cancel things. So 0.45 and negative 0.45 will get cancelled. So we will have 0.45 minus I 0.44 divided by minus I 0.88. 0.44i plus 0.44i is 0.88i, and there is a negative. If I multiply and divide by I can get rid of the imaginary number in the denominator. I'm doing the same thing that I did earlier. I'm multiplying and dividing by the conjugate of the denominator. The conjugate is I times 0.88 divided by I times 0.88. Good. Let's see. What is the denominator? It'll simply be 0.88 squared. Distribute the I times 0.88. We will have 0.45 times 0.88 multiplied by I plus 0.44 times 0.88. Good. I have a 0.88 in common, so I have I multiplied by 0.45 plus 0.44 divided by 0.88. Yes, what is that value if you divide each part by 0.88? Up.
It's 1/2.
Oh, this is 1/2 here, 0.5 plus. Slightly bigger than 0.5.
Slightly bigger, yeah.
0.5. Good. Okay, from all that work. Now, C1 is 0.5 plus I times 0.51. C2, 0.5 minus I times 0.51. Once again, in my derivation, I said alpha, C1 is equal to some alpha plus I beta. If that is the case, C2 would be alpha minus I beta. And for those alpha and beta values, when I plug it in the difference equation, I would end up getting this. So we have everything. Alpha and beta would simply be the real and the imaginary parts of C1.
So alpha is 0.5 and beta is 0.51.
Exactly. Can I raise this? So 0.5 cosine 0.776J minus 0.51 sine 0.776J. Right. I mean, they are very close to each other. Right? We can simply call it 0.9, but it's okay. What should psi 0 be?
Just 2.
2.
Shouldn't it be 1? Shouldn't it be 1, isn't it?
Psi 0 must be 1, always, right? Is it 1? So psi 0 would be 2 divided by 1.584 raised to 0. 0.5 cosine 0. 0.51 sine 0. Yes. Cosine 0 is 1. 2 times 0.5 is 1. 1 divided by 1 is 1. So now that we know psi naught, and we got 1, and in other words, we didn't mess up along the way. We had some hiccups, but we fixed it. So it has to be a 2 or it's way. Now we can find psi 1, psi 2, and psi 3. Go ahead and find psi 1, psi 2, and psi 3. You know, of course, it'll go all the way up to infinity. So what is the value of psi 1? Just have to plug in j equals 1 in that expression. What do we get?
0.623.
Psi 2?
0.387.
Psi 3?
0.241.
And psi 4?
How did I get this?
Did you get psi 4?
what did you wrong?
Well, these values are in degrees. Yeah, so we want it in radians. So what is the value?
Negative 0.0005.
Yeah. And the next one?
Negative 0.399.
Next one?
Negative 0.3594.
Okay. I want you to keep the rest as is. Now, I'm going to erase this side. Last time I mentioned something about a system frequency. And I said that you have this oscillatory behavior. If you look at our ACF, it sort of went like this and it eventually hit 0. So when you see a behavior like that, naturally you would have complex roots. And we have complex roots in this case, so there has to be some oscillatory behavior. And I mentioned system frequency last time. So the system frequency in this case, 2 pi f, and that should equal beta. So f is our system frequency. So f would be beta divided by 2 pi. Theta is 0.776 divided by 2 pi. And f would be equal to 0.124.
Yeah.
Okay, so that is the frequency. And how is the period related? Well, the period is simply the inverse of frequency. So 1 over f. And what do you get? 8.09, so approximately 8. Good. Now, so the oscillatory behavior is going to have a cyclic period of 8. I want you to pick up your calculator. So count the number of negatives, number of positives, and the next time you hit positive or negative, tell me what you get. So we found our period to be 8, right? So to complete one full cycle, it will take 8 discrete time values. So if I start at 2, count 1, 2, 3, 4. Yes. 1, 2, 3, 4. 4 negatives, 4 positives, total 8 points. Next time it hits negative. 1, 2, 3, 4. 1, 2, 3, 4. 8 time points, full period of 8. Back to negative. 1, 2, 3, 4. 1, 2, 3, 4.
You said we started at 2?
Yeah. You may ask me why. The reason being, if you go back, negative time values, you will see 1, 2, 3, 4. 1, 2, 3, 4, and so forth. And this is approximately equal to 0. So when we start at 2, you will find the period to be in sets of 8.
So,
Now do you see what the system frequency
wait,
is?
so we just ignore 1?
So A are 2 more, so 2 steps afterwards.
Okay. Wait. Just clear, we ignore 1 because it's an AR.
So we have a causal system with explained system frequency and all that. So I can express the AR model, or I say as the psi values multiplied by the error terms. So the first one would always be 1 minus 0.0005 epsilon t minus 1 minus 0.399 epsilon t minus 2 minus 0.3594 epsilon t minus 3 and dot dot dot. Good. So that is the MA infinity version.
And that's why the one is considered zero. Okay.
Right. So how do we get this? We simply do 1 over VZ, write it as a sum, and these are the sine weights. So I can write our time series that we started as an AR2 model in terms as an MA infinity model. Does that make sense? So there is a connection between the two. That's why invertibility and causality